Okay, so I should be recording physical optics, pre-response problems. The very first one is from 1975, B4, and it gives us a screen and a 1 slit. And then if you scroll on down, there's a screen and a 2 slit. And they want you to sketch a graph of the intensity as a function of position for the pattern formed on a distant screen. And then they want you to do the same thing, but this time they want it to be the 2 slits. Okay? So what I did was I said, well, it's really hard to draw a graph with this little tool that I'm using, so I just went to a Word document and I said, well, here is my 1 slit. So it's most intense right there where the slit is. And then you get farther away from the slit and you get less intensity. Okay, so with a 1 slit you get a very wide band that's very bright. And then there's your dim spots, destructive interference there. And then there's another bright spot. It's not near as bright as this center one. And then there's another dim spot. Okay, so very wide, dim, a lot more narrow and not as intense for a bright spot, and then there's my dark spot. Now if it has 2 slits, the peaks are much closer together. So there's my intensity right in the middle. That's my central maxima. Here's my first one. The second peak is the second order maxima, and here's the second order maxima here. And so they spread out much more than here because there's 2 slits. Alright, so hopefully that makes some sense. Now I'm going to pause and get moving. Okay. Then they give you 1980 B4, and they give you a graph in Part A, and it says in the graphs that follow, a curve is drawn in the first graph of each pair. For the other graph, so for here, in each pair, sketch the curve showing the relationship between the quantities labeled on the axis. Your graph should be consistent with the first graph in the pair. So you have to kind of think about what you're doing there. And I'm hoping that I can put my hands on all the hard work I did to get you some answers. All right, so here we go. So what I did was I drew my answers. So hang on, I think it might be better to take a picture of these as well because it's going to be hard to draw a graph with this little tool I have. Okay, so here is my intensity. I have 2 slits that are a distance d apart. The screen to the light source is 1 meter. And I have another time they want me to graph the intensity on a light on the screen 1 meter from a large number of slits this time. Each of them are a distance d apart, but there's a whole bunch of them. Alright, so the picture for that is going to look like this right here. Now I'm wondering if I can make it a little bit bigger. Let's see. Think we can zoom it? Yeah, here we go. Alright, so here's what it looks like. Here's those slits. Okay, and so the maxima are at the same location as before. The maxima are more narrow and well defined, and then the minimal intensity occurs right here. I have a little bit of light, very little light, pick up more and more light as I get closer and closer. Again, it minimizes to 0, maximizes all the way up. So that's what that graph would look like. Okay, so Part B says we have 2 slits. They're distance d apart. This is 1 meter from the screen to the light source. So Part B says we'll do the same thing. We're going to keep the light source 1 meter from the screen. This time we're going to have 2 slits again, but they're going to be twice as far apart, and so they want a graph of that. All right. So again, I went and said, well, I can't draw a graph on my little board that I'm using, but what I can do is I can show you this picture of what the answer should look like. Okay, so spacing D of 2 slit arrangement doubled. So what happens is this value is going to go up by twice as much, so this angle here is going to be half the size. And so the first maxima occurs at half the distance away as before, so there's my first maxima. And then I have these getting much farther apart. That's that angle that we were talking about being much wider than those other the other picture that I showed you. All right, so let's minimize that. Now let's see if we can go on and look at, okay, here's the next one, 1985. Okay. So I said, well, goodness gracious. 1985. Alright, here's my pin. Ugh. But I'm not at the right place, so let's do that again. Alright, so this one says that we have light of wavelength 5 times 10 to the minus 7th meters in air is incident normally on a double slit. The distance between the slits is 4 times 10 to the minus 4th meters, and the width of each slit is negligible. Bright and dark fringe are observed on a screen 2 meters away from the slit. Calculate the distance between 2 adjacent bright fringes on the screen. Okay, so I said, well, let me figure everything out and see what I can find out. So I knew that I had my equation, m lambda equals d sine theta, or I could call it x over L. And I'm going to assume with these tiny, tiny distances that angle is sine theta would be very close to that approximation right there. All right, so I said, well, here's my wavelength. Here's my lambda. 4 times 10 to the minus 4th meters is my distance. My 2 meters away is my L. And so if there's a bright band here and a bright band here, this distance here to here is what we're calling x, and that's what they're asking us to find. All right, so we want to find the distance between 2 adjacent bright fringes. So bright, bright, next door neighbors, how far apart are they? All right, so I said, well, m was 1 because I was looking for constructive interference. My wavelength was given to me as 5 times 10 to the minus 7th meters. My distance of separation was given to me as 4 times 10 to the minus 4th meters. My x is what I'm trying to find out because that's the distance from maxima to maxima, and they are the screen to the light source is 2 meters. So I solved for x, and when I solved for x, I got 2.5 times 10 to the minus 3 meters. All right, so that took care of that one. Okay, next one we have is 1991 B6, so let me see if I can scroll down and get that one picked up. Alright, so here we have some light. We have 2 slits again. We have a photoelectric detector, which is y distance away from this center. We know this distance from here to here is L, and this is the screen that we're taking all of our measurements on. Alright, so 1991 says light consisting of 2 wavelengths, lambda A, 4.4 times 10 to the minus 7th meters, and lambda B, 5.5 times 10 to the minus 7th meters, is incident normally on a barrier with 2 slits separated by distance d. The intensity distribution is measured along a plane that is 0.85 meters from the slits as shown above. The movable detector contains a photocell whose position y is measured from the central maximum. The first order maximum for the longer wavelength occurs at y is equal to 1.2 times 10 to the minus 2 meters. They want us to determine the slit separation d, so we're looking for that value right there. Well, that's not a real big deal. We can do that. All right, so all I said was, well, m lambda is equal to d x over L, and that's what I'm looking for right there. So m lambda was just simply going to be 1 because it was constructive interference. My wavelength for the longest one is what I'm going to deal with now. Lambda, lambda b. So lambda b was given to us as 5.5 times 10 to the minus 7th meters. And you know what I messed up? We're not looking for x. They give us that. I lied to you. We're looking for d if I read it. Yeah, slit separation d. So equals d. And then they tell us from here to here is a distance of 1.2 times 10 to the minus 2 meters. And that from here to here is 0.85 meters. So if I do the math correctly, when I did that, I got my distance of separation to be 3.9 times 10 to the minus 5 meters. So that was part A. Part B says, at what position YA does the first order maximum occur for the shorter wavelength? All right, well, let's do part B. So I said, well, part B, I still have m lambda is equal to d x over L. All right. And this time I'm looking for D. They want to know what is this going to be when I use the shorter wavelength. So it's still constructive interference. Lambda this time is 4.4 times 10 to the minus 7th meters. I know the distance of the separation now because I found that right there. 3.9 times 10 to the minus 5 meters times x, which I have no clue what it is, over L, 0.85 meters. And so the distance from here to here for the shorter wavelength is called x, and that value comes out being 9.6 times 10 to the minus 3 meters. Alright, so that's very doable. And that takes care of 1991 B6. I'm going to stop and post this one, and then we'll come back and do 1996 and a few more.